Okay, hello everybody. It seems today is only online. And today's section 11.1 computation of areas. First of all, I recall that we know how to compute area of a specific curvilinear trapezoid. So, if we have a function which is non-negative, y equals to f of x is non-negative on an interval a, b, then area of, so we consider figure which is bounded by x equals to a, x equals to b, y equals to 0, and y equals to f of x, the graph of that function. And recall that we suppose f of x is non-negative for all x in AB. And I want to discuss now the question how to compute the area. And of course, the first question should be, what is area? And we'll consider this question in more details in next semester, because now our course is called univariate calculus, right? And area of two-dimensional figure, Что, вы плохо крутитесь за мной?
Не знаю.
Ну что, отклонить, наверное?
Я могу, я такого не.
Давайте отклонить, да, не надо. Okay. So, the question about what is area of a planar figure, that is a rather complicated question in general, and we'll discuss it later in multivariable calculus, because it is related to what is Jordan measure. In fact, area is a particular case of Jordan measure. But as a preparatory thing, we can accept for a while that what is area. So, the area of, consider figure, let it be D, right? That is D. The area of D is a number S which satisfies the inequality let's say u less or equal as L less or equal S less or equal U where capital L is the area of how to say polygonal, let's say, domain of a polygonal domain, which consists of an arbitrary polygonal domain, which consists of several rectangles with horizontal and vertical sides and contains in D. U is the area of an arbitrary polygonal domain which of an arbitrary similar polygonal domain which contains D. Sorry, here I think I should write and is contained in D, and here which contains D. So you see, L is an area of some polygonal domain which is inside, right? Inside D. U is area of a polygonal domain which contains D, so outside. And obviously for any partition P, for any partition P, the lower and upper Darboux sums are examples of such L and U. Because remember, what is lower double sum? Lower double sum, how it was defined? We took a partition, right? And then we took infimum of the value of our function on every such a small interval and multiply it to the length of this interval. So lower double sum is area of such rectangular domain. And okay, you see arbitrary rectangular domain which is contained in D, is a part of D, right? Satisfies also this presentation. I mean, if you have arbitrary rectangular domain, then you can find a lower double sum which is between this rectangular domain and our figure. Also, maybe you can ask me, but it may happen that there are many such numbers, right? Because who knows, maybe there are many numbers between arbitrary L and arbitrary U. In principle, it might happen. And then it means that the area is not defined. So the number should be unique. The unique, maybe important, is a unique number. So, of course, you can ask me how we can know if such a number is unique. And that is another question, and we'll consider it in more details in next semester in multivariate calculus, because that is quite important thing. For a while, okay, we have some geometric intuition behind, right? So you see, lower double sums, they are area of such rectangular domains, polygonal domains, right? Polygonal domains, specific polygonal domains. You see, they are formed by rectangles with sides horizontal or vertical, right? So we take several such rectangles, and they are rather specific, of course. But you see, because of three sides of our figure, they are straight lines. So indeed, in such a way, we can include all such areas of arbitrary polygonal domains in our consideration. So, and now recall, we had a necessary and sufficient condition for Darboux integral. And this necessary and sufficient condition, what it says? The function is integrable if and only if for arbitrary epsilon greater than 0 there exists a partition P such that difference between upper and lower Darboux sums is less than epsilon. look at this necessary and sufficient condition. That was a necessary and sufficient condition for a function to be integrable. Now look, if a function is integrable, then what happens? It means that we can find such polygonal domains that difference between those numbers u and l is as small as we want, right? So you see, u minus l will be as small as we want. So difference between those numbers will be arbitrarily small. Then certainly there exists a unique number, right? Which is strictly between all of them. I mean, strictly not strong inequality, no. Just which is greater or equal than arbitrary lower Darboux sum and less or equal than arbitrary upper Darboux sum. So there exists a unique number, and it is natural to call this unique number an area. So this is the area of a figure. So what is the area? Unique number which is between areas of arbitrary inner domain, inner rectangular domain, and outer rectangular domain. So upper Darboux sums, they will be like that. These are areas of those upper rectangular figures. They form upper Darboux sums. Those sums. So it means that hence I can write like that. Hence the figure D has an area if and only if f is integrable on AB. Moreover, the area of D is equal to integral from A to B f of x dx. So that is just from the definition of the integral, I mean from the definition of Darboux integral, better to say. The definition of Darboux integral gives immediately this geometric application. Of course, one can consider, instead of y equals to f of x, you can consider, for example, x equals to phi of y. Doesn't matter, right? So it means that what you should do? You have x, y, you have a graph, and then what you do? You take, let's say here C, over there D, and that is x equals to phi of y. So it is non-negative when y belongs to CD, and then the area of such a figure is equal to integral from c to d phi of y dy. Formally it is a little bit different, but of course it's the same. Okay. Also, okay, for parametric curves. Yeah. If you compare those two expressions, look, for example, recall y equals to f of x, and we consider integral f of x dx, right? So we have integral y dx, right? And then if we have x equals to, let's say, psi of t, y equals to phi of t, so parametric curve, then how we can compute the area? Just substitute y and x, and it gives integral if t varies from, let's say, q naught up to t capital T, then we have integral from t naught to t, and then substitute so phi of t psi prime of t dt. Analogously, you can look at this equality, but here you should be more careful because you see, when maybe I will not mention it now. Let us keep it. So that is an example how to compute parametric domains. Maybe I will not talk about it more at the moment. So let us consider another example. So another example is computation of areas in polar coordinates. So that is still in this section. Now you see we have consider a curve in polar coordinates. It means r equals to r of phi, where phi varies from, let's say, phi 1 up to, better to say, phi naught up to capital Phi. Let it be like it was for parameters. Polar coordinates, what are polar coordinates? Polar coordinates r equals to x equals to r cosine phi, y equals to r sine phi. So it means, look what happens. So if we have usual Cartesian coordinates x and y, so let's say we have a curve r equals to r of phi. Fixing phi means that we fix a direction from the origin. So that is phi naught, this phi naught. And terminal value is capital phi. So we want to discuss now area of the figure which is bounded by phi equals to phi naught, phi equals to capital Phi, and r equals to r of phi. Phi naught between phi and capital Phi. So it means, look, phi equals to phi naught is a ray, this ray. Phi equals to capital Phi is another ray. And r equals to r of phi is a curve. Like that. So we have for arbitrary value of phi, look, if you take arbitrary intermediate value phi, like that, then this r is distance from the point of our curve to the origin. Phi varies. For any value of phi we have different distance, right? So distance varies and it gives our curve. So for arbitrary ray from the origin we have unique point of intersection of that ray with our curve, for sure, because of that is just when we write that notation. So it means that r is a function of phi, polar angle phi. So how to understand the area of this curve? We'll proceed in a similar way. So it is not clear why we can do it, but we accept it for a while without proof, without rigorous proof. So how to compute the area of such a curve? So this is the curve which we consider, right? So how to compute it? How to compute it? If we consider an arbitrary partition P of our interval of phi now. phi naught equals to just phi naught less phi 1, phi n equals to capital phi. Phi naught is the initial value and it is phi naught. So, what it means geometrically? It means that we consider several values of phi, like that, like that, like that. We consider several values of phi. Now, look at L of P Now the question is which function we should substitute here. So I want to write lower Darboux sum, right? Lower Darboux sum for a function which depends on the polar angle phi. Look, we look geometrically like we did before. So I want to replace our figure by some simpler. Okay, what is simpler? Simpler for calculation, what we want to compute. We want to compute area, right? So we want to replace our figure by some figure which is simply from the point of view of computation of area, right? Look, what is simplest area of such a kind? That is a sector, right? If you have a sector like that, right? So capital R sector, right? Here we have angle alpha. Then what is area of this sector? We know from elementary geometry, right? What is it? So if alpha equals to 2 pi, then what we have? Area of the full disk, right? Area of the full disk of radius r is equal to pi r squared, right? So area will be pi r squared. So for arbitrary alpha, what we have? Alpha over 2 r squared, right? So let us refer to elementary geometry here. So we know area of a sector. So the simplest figure, as I said, is such a sector. Now, here we have no sectors in general. I mean, that boundary of sector has a not constant distance from the origin, right? So distance from the origin varies. When we travel along the boundary, right? When we travel along the boundary, the distance varies, right? So, but what we can do? Let us take minimal. So, minimal distance. Minimal distance, right? So, replace our area by those sectors, right? So, we replace our figure by a figure which consists of several sectors. Several sectors. Let us compute area of each of that sector. Look, so let me consider one of them, one of those sectors. One of those sectors is described by phi j minus 1 less or equal phi less or equal phi j. So these are boundaries in rays, right? And what is circle area? I mean, arc of the circle, right? So here we have an arc of a circle. Which circle? What is radius of this circle? Radius is equal to, so r equals to infimum for all phi in our interval of r of phi. So we have minimal value of r, right? And we take a circle with this radius. So when we consider this figure, that is a sector, right? Precisely sector. And this sector is inside our figure for sure, right? What is area of this sector? Area of this sector is equal to what? This infimum, right? Let me call it, okay, infimum r of phi in phi j minus 1 phi j squared times what? Angle over 2, right? What is angle over 2? Angle difference between phi j minus 1 over 2. That is one term. One term is area of this sector. And if we add all of those sectors, then we obtain what? We obtain this sum. And what is it? This sum. Look at this sum. That is precisely Leonidovich sum for such a function. Look. That is r squared of phi over 2. So, Leonidovich sums of that function, their geometric sense is area of such a figure which consists of several sectors, and this figure is inside our original figure in polar coordinates. Okay, let's have a break. Let us continue. So you see that Leonidovich sums of this kind, they have very clear geometric sense. Namely, what they give? They give areas of such figures, so figures which consists of sectors, and all those sectors lie inside our figure, our given figure, right? So you see, what is this Leonidovich sum? That is precisely the area here, this area, right? And all those lines are arcs of a circle with center at the origin. So all those lines are arcs of a circle with center at the origin, right? All others are rays, paths of rays. Analogously, what we can say about this? What is upper double sum? It will be quite analogous, right? But it will consist of areas of sectors which are greater than our figure, right? Greater than our figure. So our area S is between them, right? By the construction. Is it clear? So what we want? We want to define a number which represents the area of this curvilinear figure. Unfortunately, I have no color stocks. It would be nice to have it, but not. So maybe I'll represent in more details a small piece of our. So look at small piece. We have two rays, right? That is our figure. R is R of phi. And one sector is that one, which is included into this. The area of this sector, that is arc of a curve, arc of a circle, right? Another with supremum gives that sector, right? So we have, we have two sectors, right? One sector, area of one sector, is included into lower double sums. Area of larger sector, that one, is included into the upper double sum, right? Then what we do? On that picture, I show only one sector, right? And then what we do? We consider several such sectors, and add all of them, right? So lower double sum is for sure less or equal than the area of our figure. Upper double sum are greater or equal for sure, right? And that is valid for arbitrary partition. So we have this inequality for arbitrary partition. Hence it is natural to accept, you see, I don't use words proof and so on here, right? Because no proof yet. We should define rigorously, and that is absolutely different story. It should be done in multivariate calculus, as I said. To accept that the area of the figure. I didn't denote it. Yeah, of the figure, that figure, let it be omega, let's say, right? Omega, this figure, of the figure omega, is equal to 1/2 integral from phi naught up to capital phi r squared of phi d phi. That is how to compute areas. Okay. Next point is so it will be next section 11.2 lengths of curves. Let us start with the simplest case of a graph of a curve, of a function. So, firstly, consider graph of a function y equals to f of x. Now it doesn't matter if the function is positive or not. It's not important absolutely. Y equals to f of x. Let it be A, that is B. How to compute? Yes, there is a good question. Equal case here, right? Equal case. One, we have equality here. We have equality if r is constant, right? And what means r is constant here? R is constant here means that we have just an arc of a circle, right? So, indeed, in that case, we have equality in both sides. Yeah, that is good question. Okay. So, let's continue with length. With lengths, we can, again, it's difficult to do it without multivariate things. I need to avoid them. So, I want to understand what is length of this curve, graph of a function, right? How to compute it? What is length? And here I can give a definition because that is completely univariate. So, definition. Length of the graph of y equals to f of x, a less or equal x less or equal to b, is the least upper bound of the set of the lengths of all polygonal lines inscribed into the graph. So what it means, we take polygonal lines like that. So let's say like that, and then like that, right? So we take several points and then connect them by straight lines. Now, look, obviously, why this definition is natural? Because, look, obviously, once you choose finitely many points on the graph, right? So, what we do? We choose arbitrary points of the graph, connect them by straight lines, right? So that is how our polygonal line was formed. After that we compute the length. But look, obviously, length of a straight interval, right? Straight line interval is less than the length of a piece of graph, right? Because graph is curvilinear, right? And polygonal line connects, roughly speaking, ends of this piece of graph in a straight way, right? So obviously, length of a straight line is less than length of arbitrary path which connects those points, right? Is it clear? Look, take arbitrary 2 points, take arbitrary line, then length of this line is less than, greater than length of straight line, right? So always straight line has shortest distance, right? Shortest length, right? So now look. So it means doesn't matter how we choose our polygonal line. If it is inscribed into our graph, then it has length which is less or equal than the length of our graph, right? And the least upper bound, what it means? It means that we can approach as close as we want by length of our polygonal line, right? Okay. Then let us compute the length of that polygonal line. So let us denote somehow, let's say that is x1, here we have x2 and so on, right? So it means once again we have a partition x0, xn equals to b. Then what we do? What we do? So, what is the length of one straight piece of straight line between 2 points? So, what is it? We are interested in the length of, let's say, of a piece of line between which connects those 2 points, right? Line which connects 2 points, straight line which connects 2 points. What is length of this piece of straight line? Is the distance between those points, right? What is it? So that is precisely square root of xj minus 1 squared plus yj minus yj minus 1 squared. That is precisely length of this one piece, right? And then we add all of them. So that is precisely the length of our polygonal line, right? Length of arbitrary polygonal line, which is inscribed into our graph. Now look. Look. What I'll do with it? So what are yj and yj minus 1? By definition, what are those yj's? We took points of our graph, right? It means yj equals to f of xj. Precisely, right? So, let me compute it. That is xj minus 1 squared plus f of xj minus f of xj minus 1 squared. Then, let me do the following. So, I arranged xj's in increasing order, right? So it means all those differences are positive. Hence, I can write like that. Sum j from 1 up to n, square root of 1 plus f of xj minus f of xj minus 1 over xj minus xj minus 1. Times xj minus xj minus 1. Now, if the function f, if f is differentiable on AB, then by the Lagrange mean value theorem, there exists a point Cj which is between xj minus 1 and xj, such that f of xj minus f of xj minus 1 equals to f prime at cj times xj minus xj minus 1. I'm sorry for notation, let me change notation to xi. That is better, otherwise I'll spend time. Xi j. Then look what happens with our sum. Then our sum is equal to what? Is equal to sum j from 1 up to n square root of 1 plus f prime at psi j squared times delta xj, where delta xj is just that difference, as usual, right? As usual. Then look, what is it? That is precisely integral sum of a function. Which function? S of g p psi, where g of x equals to square root of 1 plus f prime of x squared. Right? So, look what it means. What it means. It means that what we have about length. So, let me write down what we obtained. For arbitrary partition P, there exists a choice of points xi such that integral sum is less or equal than our length. Look. Because remember, those xi's are chosen in such a way that this integral sum is equal to the length of this polygonal line, right? And the length of this polygonal line is for sure less or equal to the length of our graph. So this is valid for arbitrary partition. Now, look what happens after that. In fact, what we obtain then is that now we can conclude that if derivative of our function is continuous additionally, right? So if we suppose additionally that the function f is continuously differentiable, then what can we say? We can conclude, so if f is continuously differentiable, on AB, then this tends to what? Tends to the integral from a to b of square root 1 plus f prime of x squared dx if S, sorry, not if, S, the norm of partition tends to 0, right? So, if f is continuously differentiable, then we know what happens with integral sums, right? That is for sure. Okay. Now, what we conclude? What we conclude? We conclude the inequality with, so we have this inequality, integral from a to b square root of 1 plus f prime of x squared dx less or equal than L. Moreover, look at the picture. Look at the picture. Look at the picture. What happens with lengths if we take points x more and more often? What will happen with length? Look, it means we have polygonal line which is practically coincides with our graph, right? So you cannot distinguish between them. If you have points very often, right? Connect them by straight lines. Connect them by straight lines. What happens then? You obtain a polygonal line which is very, very close to the graph, right? But once again, of course, I have no proof. I have no proof. But these are just some geometrical observations which suggest that in fact we have equality here, and that is the length of the graph with the help of integrals. With the help of integrals. There is a formula to compute length of a graph. Of course, you can ask why equality here. We didn't prove it, right? But to prove, I should go a little bit into multivariate calculus. Not so much, but you see, we have univariate calculus now. So it means I have no tools to proceed further in that direction. But nevertheless, we can give some corollaries which are suitable for computing in more general case. So, for example, replace now, so instead of y equals to f of x, right? So replace it by parametric equations. Phi of t sorry, psi of t, let it be, x is phi of t from t naught up to capital T, right? Replace it. Then what happens with our integral? Roughly speaking, of course I should make some suppositions, but instead of that, look what we have then. So what is f prime? What is f prime of x? F prime of x is derivative of y over dx. But we know how to compute derivative of a function which is given parametrically during first semester, right? There was a formula. How to compute it? We differentiate dy over dt and divide it by dx over dt, right? So it means we divide psi prime over phi prime. And then look, we do this as a substitution into the integral, as a substitution. So make a substitution. So we suppose that a and b are values of x which correspond to values of t. What we obtain from t naught to capital T, then square root of 1 plus, replace f prime, psi prime of t over phi prime of t squared. Then instead of dx I should write phi prime of t dt. And of course it is natural to suppose that phi is increasing, strictly increasing to avoid zeros of derivative, right? Strictly increasing, strictly increasing. Phi of t is increasing. Then this is positive, right? And I can rewrite it as follows. Phi prime of t squared plus psi prime of t squared dt. That is the formula for the length of parametrically given curve. Parametrically given curve. So if our curve is given parametrically, these are parametric equations for our curve, then the length can be computed by that formula. And without proof, because I don't want even to go to R3, but if we have a curve in R3, then what happens? Still, there is a curve in R3, right? For example, you look at trajectory of a point, how it moves in the space. Then what will change in the formula? The length of that curve will be similar, but we add one more term. That is length of the curve in R3, that curve. And I think I should finish with example, not an example, but just a particular case curve in polar coordinates. Curve in polar coordinates. R equals to R of phi. Then what it means? It means that we can consider phi as a parameter. So x is R of phi cosine phi. Y is R of phi sine phi. And just substitute phi prime in 1 to the last equation. Phi prime is not to 1 in the last. I just multiply phi prime and it gives that one. Phi prime is not 1. I just multiply and it gives that one. Why I multiply? Why I cannot multiply? Phi is increasing, so phi prime is positive. Why I cannot multiply? I don't understand. Multiply phi prime inside square root. I don't understand the question. Why? Okay, so now look at this. Then x prime of phi, r prime of phi cosine phi, minus r of phi sine phi. Y prime, r prime sine phi, plus cosine phi. And then x prime of phi squared plus y prime of phi squared equals to, if you substitute, take squares and transform it a little bit, then look, we have r squared of phi plus r prime of phi squared. Very simple expression, because double products are cancelled after taking squares, and squares of r and r prime will be with coefficients cosine squared plus sine squared, and they're equal to 1, right? So we obtain the length of such a curve. The length is given by integral from phi naught up to capital Phi, square root of r squared of phi plus r prime of phi squared d phi. That is the length of our curve in polar coordinates. Okay, that's all for today. Thank you.